let's go to question 1 of the multiple choice that you took. So my goal is that by going over this problem set, that we'll review everything, mostly everything that's in there, because this test should cover everything that you guys took. So number 1, we see a blue sphere and a red sphere with the same diameter are released from rest at the top of the ramp. The red sphere takes a longer time to reach the bottom of the ramp. The spheres are rolled off a horizontal table at the same time with the same speed and fall freely to the floor. Which sphere reaches the floor first? So they drop at the same time. So which one's going to hit the floor first? What do you guys think?
The blue one,
Why do you say that?
because the red sphere took longer to reach the bottom of the ramp.
What affects the time in the air, right? They're asking which one's going to hit the time, which one's going to be in the air less time. So what affects time in the air?
Height.
Only height. So they drop from the same height at the same time. The answer is D. One thing that was interesting to me that I can now talk to you guys about is when they go down the hill, when they go down the ramp, the red sphere takes longer time than the blue one. And if they're released from rest at the same time and they have the same diameter, why is this one so much farther down? Why do you guys think?
Was it like the wood blocks?
Yeah, just like that. Their weight distribution is going to be different. This one is taking a longer time to accelerate, so it must have a big inertia. So the mass is going to be distributed away from the center. This one has less inertia, it's accelerating faster, it's resisting less to accelerating, so the mass is probably concentrated more towards the center there. Once they get here, the other question you could ask is which one will go farther and which one would have gone farther? What? Well, they leave with the same speed. So what things affect how far it's going to go? So yeah, if I want to know how far it's going to go, it's going to be v times t. And I know the time in the air is going to be the same because one half at squared. I know the time in the air is going to be the same for both because they drop from the same height. Gravity affects both the same. And I know that the velocity will be the same for both, so they're going to have the same range. Questions on this one? No? I feel like I hit lots of topics right there, so that's what I'm hoping I will do with all these problems. A 12-kilogram box is sliding on a horizontal floor. A 12-kilogram box sliding on a horizontal floor has an initial speed of 4 meters per second. The coefficient of friction between the box and the floor is 20 meters per second. The moves a distance of 4 meters in 2 seconds. The magnitude of change momentum of the box during this time is most nearly. Dang, that's a mouthful. When you read something like that and they just throw a whole bunch of information at you, concentrate on what are they asking me, and then what do I know to know. So what are they asking you to find?
Momentum.
The change of momentum. How do you find? What do we know about change of momentum? It's the impulse.
The jack fact.
Yeah, think jack fact. So it should be impulse equals change momentum equals force times time, right? So we put impulse equals change of momentum, which is mvf minus mvi equals force times time. So we have this right now. We know the mass, right? We know the initial velocity. Do we know the final velocity?
Zero? Oh, wait, no.
They don't really tell us, right? So, but we do know the other part, the FT part, change of momentum. So what is the force that's causing the change to the momentum? Friction. So change of momentum will be friction times time. Do you know the time?
2.
2 seconds. So now friction, which is the thing causing the change to the momentum, speeding it up or slowing it down. How can I find the force of friction right there?
Well, it says that it's 0.2, the coefficient of friction.
And how does that help me?
Use fun.
Yeah, I can use this awesome fun formula. So the coefficient of friction times the normal force. And what is the normal force right here?
mg,
mg. How do you know it's just mg and not like some other weird thing?
because it's loaded on a horizontal floor.
Yeah, it's horizontal. So 12 times, again, it's technically 9.8, but if you use 10 on the test, it will work out. And they don't mind you to use 10. And the coefficient of friction was 0.2. Alright, so 2 times 10 gives me 20 times 12.
24.
What? 240? 240 divided by 5, because point 0.2 is the same as divided by 5.
That's 48.
48? The answer is B, 48. Job fat. Job fat's going to be super important, just as work energy and impulse momentum. Those two connections have to be there. Question right here? No? So number 3, just by looking at this picture, what kind of interference am I going to see?
Constructive.
Constructive. So, let's see what happens. The figure above shows 2 wave pulses on a spring traveling towards each other. At time 0, at time 2, the pulses completely overlap. They're right on top of each other. Superposition. The student measures the amplitude at point A, B, C at the 3 times shown above. Which of the following is most likely? Which of the following is most likely set of values that the student recorded for X, Y, and Z? So time 0 is the beginning. Time 2 is when they're right on top of each other. And time 4 is afterwards, right? So at point B,
The outside was locked.
which side? I'm sorry. At point B, when they're right on top of each other, what should we expect right there? What should we expect? Now what? To be what? 0.5. Why? Because they're added to each other. Awesome. And then at 4 seconds, that's when they've already reflected or passed through each other. Pass through each other. So at point A, which one's going to be there? The one at point 3 or the one that's point .2,
Point three.
.3. And then the other one, the little one should be on the right, so the answer should be .5. And this is where I would be writing on the test, like, because right now trying to do it in my head is kind of hard. So X would be .5, so that's out C and D. Y would be .3, so the answer is B for 3. That's right. Oh, I love this problem right here already. Conservation of energy problem. A rubber ball with a mass of 0.20 kilograms is dropped vertically from a height of 1.5 meters above the ground. The ball bounces off the floor, during the bounce, 0.60 joules of energy is dissipated. So what does dissipated mean?
They lost.
It lost. What is the maximum height of the ball after the bounce? So what information do we know right now? When?
Beginning.
At the beginning, so we know MGH at the beginning. So we can point 0.2, 9.8, and then 1.5. That's my initial, right? So what's that going to be equal to?
.294?
2.94?
Yeah.
2.94. And then when it hits the ground, so right before it hits the ground, so that's how much at the top, and then it comes down, here's the ground. Right here, right before it hits the ground, what kind of energy does it have? How much kinetic energy? The instant right before it hits the ground. Yeah, the same that it had up here. That's how much kinetic energy is back here. And let's say that this was, and because I'm trying to review everything, let's say that this was an elastic collision. What do I know about elastic collisions? No energy is lost. So this was an elastic collision. What would be my kinetic energy the moment it bounced up, down here? 2.94, because no energy was lost. If it was an elastic, perfect elastic collision where no kinetic energy is lost. And then it would bounce back to what height then? If it was an elastic, perfect elastic collision.
1.5.
1.5. That's the height it would jump right back up to. But that's not what happened. How much energy it lost?
0.6.
0.6. So now what can I do to solve the how high did it bounce up to?
Can you subtract the places from the 2.94 and then solve for H and G?
Yeah, so we get 0.234 equals 0.2, 9.8, and then my H. So go ahead and do that. You got 10?
Pen.
Oh, you want to borrow a pen? Sorry. I have color pencils. I don't see a pen. So in previous Saturdays, I let you guys try out the problems. Or does this work better since we've already seen them, or you guys want me to give you like a chance to try them out? Sometimes just like going over how to solve them. But what do you guys think?
Like, depends on the problem.
Depends on the problem? We'll vote? Okay. So what are are we getting right here? It should be, we know D's out for sure.
We should be getting, I think, C.
C?
Yeah.
Because we're getting 1.19.
Yeah, the answer is C. I wonder if you would have tried 10 if that would have made a difference.
Yeah, I got 1.17.
When you use 10? Alright. So a sled slides down a hill with friction between the sled and hill, but negligible air resistance. So there's friction down a hill. Which of the following must be correct about the resulting change in energy of the sled earth system?
So there's friction.
There is friction. Are we doing it on our own, or am I just like going through it?
I was kind of looking at them.
I don't know, you guys tell me. Just go through it?
Yeah.
Okay. So, let's picture what happens with friction and without friction right here. So we have this sled going down this hill, and it's right here. We're talking about the energy changes that are happening. So let's picture with no friction right now, right? What kind of energy does it have at the top? Potential. Let's say it started at rest. Only potential, right? And then at the bottom? Kinetic. And what do I know about those two values? They're equal to each other. Yeah. Even if this was moving at the top, let's say it had potential. I'm sorry, let's say I had kinetic and potential at the top. And then right here it only had kinetic, which is 1/2 mv squared. What can you tell me about these two numbers?
They're equal to each other.
They're going to be equal to each other if there's no friction. All that potential energy is going to go to the kinetic. So the total energy, the mechanical energy, will be the same, yeah. Now, there's going to be friction this time, right? Are these two numbers going to be equal to each other? No. Which number is going to be bigger?
The beginning
Which sum is going to be bigger?
at the top.
Yeah, the magnitude of these two is going to be bigger than down here. By how much? By what?
By however, how much energy was lost to friction.
By however much energy was lost to friction? That's right. And then once we know how much energy was lost to friction, we can actually do work equals force times distance to find the distance it slid. If we know the force, if we know how to find the force of friction. But I'll come back to that right now. So read number 8, lettering. Does that sound right or wrong?
Right.
Yeah, it sounds exactly what I just said. The sum of the kinetic and potential energy will change by the amount equal to the energy lost through friction. Let's look at the next ones then. Let's see if they make sense. The gravitational potential energy decreases and the kinetic energy is constant. I mean, that doesn't make a lot of sense. Why wouldn't it be speeding up if it's going down? At least a little speeding up. The decrease in gravitational potential energy is equal to the increase in kinetic energy. That one would be correct if there was no friction. The gravitational potential energy and the kinetic energy both decrease. Maybe if it was like a flat surface or like something, it would be weird. Not saying it's impossible, but it would be like a really small hill. You're sliding down and eventually just come to a stop on the hill. So yeah. So if we know how much energy was lost in the system, what was called, if we work equals the change in energy. Work equals change in energy. In this case, there was a change in energy. change to mechanical energy. So that change in energy, what was the force that was causing it? Friction. So if we know the change in energy to the mechanical energy, we know the force that was causing it, we can solve for the distance over which that happened. So again, trying to review as many things as possible. This one's for you, Adriana. How do I find the force of friction on a slant? Well, how do I find the force of friction to begin with?
The coefficient of friction times the normal force.
There's the normal force. And if I'm on a hill, how do I find the normal force?
Cosine theory,
So which direction does it point?
perpendicular to the
Perpendicular to the
surface.
surface. And you told me it was what?
Cosine of the angle.
Cosine of the angle? What's wrong with that?
Oh, you still need the mg.
Yeah, I was hoping. I don't want you guys to just put cosine of the angle. I'm scared because some of you guys have done that in the past. You guys just you forgot the mg part. This is mg, and then this right here is sine of the angle mg. Cool. 6. A student sets an object attached to a spring into oscillatory motion and uses a position sensor to record the displacement of the object from equilibrium as a function of time. A portion of the recorded data is shown in the figure above. So when you guys see pendulums or strings, immediately start thinking, sometimes things that you forget are, things about the period and things that affect the period. So in a spring, the K is going to affect the period and then the mass is going to affect the period. And you guys have that equation available to you. Is that going to be necessary? No, because I don't know. This is like the second time I look at this, I'm being completely honest. The speed of the object at time 0.65, so right in the middle of 6 and 7, is most nearly equal to which of the following? So why don't you guys go ahead and try that one right there. This one's a tricky one. So go ahead and look over here. I feel like a lot of times, I'm not sure, but in my experience, I feel like the English department here doesn't really get really into this until you get to calculus. So, what were you guys thinking?
C.
Yes.
C.
Why were you thinking D?
Because it's like at 6.5, it's like starting to curve and not like really straight.
Okay. So, B and C both seem like good choices. I'm glad that nobody said A. The value of the graph at 0.65 would not be the speed, that would just be its position, is a position graph. So, so we're looking for the speed, so you want to look for the slope. And B says the slope from the origin to 0.65. C says the slope where the graph crosses the time near 0.65 and a slope of the line connecting the point where the graph crosses the time axis near 0.65, so at the 0 mark, to the point where the graph is at 0.65, which is very good. That will give you, and here's the weird part. This is a calculus thing. This will give you the average speed right there. What you guys found is, so 0.6, 0.7, and it goes like that, right? Something along those lines. Like that. And you guys found the slope, a line of a slope that goes through there. So that right there will tell you like the average speed, because you're taking all these points into account. This point, right, this value, this value, this value, this value, this value, this value, dividing over that. So in calculus, they call it a tangent line. The tangent line is the slope at a very, very specific spot. So the tangent line is the slope through that very specific spot. They call it the instantaneous velocity, the instantaneous speed. So this gives you more like an average of a speed over that amount of time, because you're taking the slope right here through right here, where on D, it's like the very specific slope at that moment right there. But you guys had all the right concepts, so it's all, if you guys see the slope of the tangent line best fit, they mean like at that very specific moment. So number 7, the total distance traveled by the object between, 6 was D, by the way, D. But C is the next best answer. The total distance traveled by the object between 0.35 and 0.40 is most nearly, so 0.35 and 0.4. What are you guys putting right there?
2.
Yeah, 2. That one should be one of those, like, we don't waste a lot of time on this one. Who does not see why 2? Because what kind of graph is this? A displacement. And what is displacement? Well, not really distance traveled, but how much it has moved from a certain position. So at the beginning of 0.35, where are you? What position? Oh, no, but what's the value of your position?
1.
0?
No, we went 0.5.
0.5, I mean, 0.5 at the most, right? And then at 0.4, where are you?
3. 2. No.
Like negative,
You like that,
negative 2, negative 3, something like that, right? So when we're talking about the displacement is how far you have moved from a certain position, and the negative just means the direction. So this thing moved from position 0 to position -2. And then it was going to come back this way, and it was going to go that way. But in that moment, it went from 0 to -2. So in the time of the total distance, that's always going to be a positive number for like how far total did it move. Yay? The frequency of the oscillation is most nearly, man, I love this problem right here. How do we find the frequency?
Speed equals wave rail, that's frequency.
Okay, so this guy just said, and let's review, because I like everything that you're saying. Speed equals wavelength over frequency, but we don't, I mean, you're gonna divide by the wavelength, maybe, because then you said,
But or
or
1 over the period?
1 over the period gives you the frequency. Can we find the period from this one? What's the period right here? What is it?
6.4.
Go ahead and use the crest.
No?
Yeah, 0.5. Did you use the crest?
Yeah.
That's what I used, the crest.
There
Cause-
is a trough.
Oh, the troughs?
Yeah.
Oh, okay. I use the crest. From one crest to another crest is a wavelength, one cycle. So 0.2 to 0.7 gives you 0.5. So 1 over 0.5. What is that, 2? No, 2? I don't know, I don't have a calculator.
Yes.
2. So we have an object. It's moving to the west at a constant speed. So what I want you guys to, even before I'm doing all this stuff, when you're reading these problems, start trying to kind of think, where's this problem headed? If it's moving at a constant speed, what should I be thinking? Forces are balanced, acceleration is 0. Moving to the west, I gotta be thinking negative direction maybe, stuff like that. Three forces are exerted on the object. One force is 10 newtons to the north. Another force is 10 newtons due west. Never eat sour waffles. West. What is the magnitude and direction of the third force if the object is continuing to the west at a constant speed? Dang. This one's a good problem right here. So, what do I want all my forces to be? Balance, right? So, let's look at the first one and see if it balances it. So, 10 to the, let's draw the direction, northwest. So that's going to be this way, right? Is that going to be pretty balanced?
No.
No.
No, because there's nothing balanced. I mean, it seems like it's going to be a lot to the left, right? I mean, this side, we split this one into its components, and that's a lot of this way and not a lot of that way. So there will be a net force to the left right there. And what you said, you already started making the prediction that I wanted you guys to see.
Yeah, because essentially what you said, because it's point, the questions they tell you to, they point at like at X.
Yeah.
So then from there you gotta split into its components,
Yeah.
find the closest.
So if I wanted to balance, in which direction would I, now that we see what we have to do, in what direction would this force need to point in order to balance?
Southeast.
Southeast, boom, knock out 2 of them already.
Yeah, I got that far and then I just guessed.
Then you just guessed.
Yeah.
So north, A and B are out, so 10 to the third and 10 to the second. I mean, it's like a math thing right here, guys.
Yeah.
We're, okay. So, this is vector addition right here, which in trig you learned, right? No? You should have. So if I add both these vectors right here, now we're going opposite. These two together, I can find the thing right here. So I can find this vector right here from putting these two together. And what does that give me? So it'll be 10 squared plus 10 squared equals C squared, right? So then you solve for this C right here, and that's gonna give you the value that should be in this direction, which will be D. D right here. But you got it down to those two using physics, then it just became like a math problem right there. Sorry, math teachers. So, a block A of mass 2 kilograms is released from rest at the top of a 3.6 meter long plane incline with 30-degree angle shown as here above. After sliding the horizontal surface, block A hits and sticks to block B, which is at rest and has a mass of 0.3 kilograms. Assume friction is negligible. The speed of the blocks after the collision is most nearly, dang, I love this problem. This problem's sweet. Go ahead and try it on your own. I like this review, going through these problems. I feel like we're hitting a lot. Watch this video. People at home, watch this video.
I don't know if they're not gonna put it, that's the thing.
I know. Keep watching this video.
There you go, that's good.
Just clickbait them or something.
What?
Clickbait them or something.
Clickbait them.
Yeah.
Man, and I'm gonna put it on Edpuzzle where you can't fast forward, and it's like, at the end of the video, Mr. Estrada farts really loud. So loud. And then his pants turned brown, so I think something extra happened. Watch the video to find out. I don't know.
And then at the bottom, PS, don't think the Taco Cabana burritos.
No, I like Taco Bell burritos. I don't want to get on their bad side. You're the guy that made the video. We're not sending it to you anymore. Man, this is a good problem. It's long. Who's solving it with energy? Who's solving it with kinematics? I'm going the kinematics route, but I would have solved the kinematics route because I hate the trig part. Maybe if I was better at it. find the V?
Mm,
That's the key to this problem.
I'm just trying to see.
Time.
You don't need time though.
The equation is displacement times time. I'm just gonna do it now. Where's that?
Why is it 8V?
Cause I'm dumb. I also was a math student at the school, remember? Oh, burn math teachers! Don't stress to math teachers though.
Question is, are they still here?
What?
Are they still here? Same as I taught you.
No, only Miss Chacon is the only one I had that's still here. Alright,
We took a video of them saying that.
go ahead and look up here. I don't, it's the inspires that I hate. I hate inspires. Alright, so people, let's go over the energy people first. So, the people that did energy, how did you solve for the, sorry, I skipped over this part, because I feel like everyone did it. Hopefully everyone set this up right here, plugged in, you were looking for this V, and you realized, well, I need to know the velocity that this thing was at the ground by. And there's no friction, so the velocity it hits at the bottom, that's going to be the velocity it sticks to, that it hits at. So if I wanted to know the velocity at the bottom, what kind of energy did I want to know at the bottom? Kinetic, 1/2 mv squared. And at the top, what kind of energy did I have?
Potential.
Potential, mgh. So what do I need to know to solve for this? The height. So you have to do some SOHCAHTOA, because you know that the hypotenuse is 3.6 to find the h. So you have to use tangent. Tangent of 30 equals TOA. Opposite. Oh no, not this one then.
I use sign.
Sine, it has to be sine. Sine, which is opposite over adjacent, over hypotenuse, which is 3.6. Maybe I should use x instead. So sine of 30.36 times sine of 30. What did that give you?
3.5.
What?
3.5.
3.5? Maybe your way might have been easier. I don't know. So now we know the height is 3.5. Everybody with us here? Actually found the height. So now we know that the potential energy at the top equals the 1/2 mv squared at the bottom. We can just take out the masses, so we get 9.8 times 3.5 equals 1/2 v squared. So we have 9.8 times 3.5, assuming 3.5 is right. I'm going to multiply that times 2. And then I'm going to take the square root there. And I get my velocity at the bottom equals 8.28. Is that what you got?
I got 8.36.
So like 8 point. How'd you get that? Oh, because you use the masses too also?
Oh no, I use 10.
What? Oh, you used 10?
Yeah.
Okay, whatever.
Oh,
I mean, it won't, that's why the choice, once we solve it, it should be fairly obvious. So, cool, that's one way to do it. My way that I did it, because I didn't want to go through this mess, although, and after you did it, I was like, oh, it's not that bad. It wasn't that bad. I went ahead and add this block up here, right? And I wanted to find VF. What other things do I know in kinematics? I'm looking for VF, but I know VI. What's my VI? 0.
Negative distance.
I know my change of x equals 3.6. And all these problems, all the kinematics equations use what variable? Acceleration. VF equals VI plus AT squared. And then, like, all of them have acceleration, so I need to solve the acceleration. So how do I solve the acceleration right here? There's no friction, right? So all the acceleration is based on sine of the angle mg. Oh, mine's gonna be longer. I take back, yours is better. So acceleration equals the net force or the mass. The mass being what? 2. And then the net force being mg sine of the angle. So when I put in mg sine of the angle, God, these calculators are the worst. Second trig sine of 30 times 9.8 times 2 gives me 9.8 divided by 2. My acceleration equals 4.9. So now I can do VF squared equals VI squared plus 2A change of x. I need to know the time because there's an equation that doesn't need time. So I have 0 plus 2, 4.9 gives me 3.6. I do that, take the square root, and then I still get this number. It's longer. I agree. Yours, the energy method is better. Which I thought it was gonna be simpler. I just didn't want to do this, but always energy method first. I said that before at the beginning of the year, and I'm saying it now. The energy way is so much better. Anyway, once we get that there, what was the answer?
I think B.
What problem is this? 10? You guys got 3.2?
Yeah, I got 3.31,
Yeah.
but I just assume that it's closer to 2 than 8. What did you get?
I got 3.34. But yeah, like I just assumed it's supposed to be 2 and 10.
Is it B?
Huh. It says it's supposed to be 8.
What?
What?
No.
Oh.
Okay.
How?
I don't know right now. Again, this is the first time I look at these problems in a long time. Go on.
Should
I'll
we
come
get a
back
different
to it.
calculator?
Hmm?
Maybe it's the calculator the way it's rounding.
Well, let's see right here. 2
Because I didn't round to the
times
end.
4.9 times 3.6 gives me 5.28. V squared, I take the square root of that. Huh.
Don't you also have to find the inelastic collision?
No, 'cause it says they stick together.
That's why.
No, this is the equation right here for an elastic collision.
Oh, that's.
The one where it's MV plus MV, 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 that's the one where they stay less, when they don't stick.
I got, over here, my V was 5.93. So 5.93 times 2 divided by 5 gives me 2.37. So mine worked out.
What?
But wait, yours should have worked out too. Did you do this wrong, maybe? 3.5 seems a little too close to 3.6.
That's what I was thinking.
Wait a minute, how can it be?
I didn't,
I just kind of trusted you on
yeah,
that.
I didn't solve for sine either. Let me see.
I mean, both methods are valid. Where's the trick? Second,
1.8, isn't it? I got two different, the first time I did it, I got 3.5.
sine of 30 times
3.6.
3.6, 1.8. There it is, that's the problem.
Ah. So we, yeah, because I didn't do sine, because you
Yeah.
said it was already. Okay.
Yeah, well, so the first time I did it, I got 3.5, and then that didn't look right to me either.
But you just went with it because you're in a rush?
Oh my
No,
God.
I understand, like, and that's a danger when you don't have time to do the calculations twice on the test. But, I mean, all the physics we did was right, it's just right here.
I mean, we understood it, so.
Yeah, so, I mean, if we use 1.8 over here, you know, and I thought, man, that's
It's
that's
really
gonna be a really
close.
steep hill. Like, really steep. 3.5 and 3.6. You should have questioned that.
Okay.
I want to say you're bad, but I'm the teacher, so I feel like it's mostly my bad. 11. A student is asked to move a box from ground level to the top of a loading dock platform. As shown in the figure above in figure 1, the student pushes the box up an incline with negligible friction. In figure 2, the student lifts the box straight up from the ground level to the loading dock. In which case does the student do more work on the box and why?
Can we go over this one?
Yeah.
So I was confused.
What is work?
Forced
And
energy.
change the energy.
Oh, change
And
in
forced
energy.
and.
When I say change in, when it is work, I always want you guys to say change in energy. Because that's what it is. How do you find it?
Oh.
Then it's force times distance.
Or energy.
So work, what was the change in energy? What kind of energy change do we see in this problem?
From kinetic.
Well, that's not what when we mean, okay.
Oh,
That's an energy transformation,
you're talking about
but
work.
what work, when I mean change your work, I mean either from kinetic, one velocity to another velocity, or one height to another height. So change in work, by change in work, they mean in a single type of energy. So work equals a change in potential energy, or work equals the change in kinetic energy. When we talk about energy changes, maybe I shouldn't have said energy changes. They're more like transformations, I guess. I don't know. I don't know, like I do know, I just don't know how to like put it technical for you guys. But right here, we're seeing a change in potential energy. In both cases, it's starting at at zero, let's say zero potential energy, it's on the ground, and then going up to a certain height. So which one had a greater potential energy change?
Isn't it the same?
I heard B.
Yeah, it should be the same.
It should be the same. They both went up the.
The same
They both started. Let's erase this junk.
Both started 0 and they ended at D equal.
So work equals change in energy. In this case, work equals change in potential energy, mgh final minus mgh initial. So what was the initial potential energy for both of them? 0. So let's see which one did more work. They both have the same m's, right? They both have the same g. Which one had a bigger h?
Height, they both have the same age.
So they both did the same amount of work. That's why the answer is D. But what ramps do, and it talks about it right here, ramps are a simple machine.
Yes, I can change.
I was going through all 6 ones in my head. So the way, what simple machines do is that they decrease the amount of work that you guys need to do. So in a ramp, what it does is work equals force times distance, right? Yeah? So what a ramp does, it increases the distance
But it decreases.
and decreases the amount of force that you have to put in. Because in one of them, look at the distance that you have to travel. You have to travel this distance, right? And in the other one, you have to travel this distance. So by taking the longer path, you're putting in less force. But the change in energy, the work, is the same. But the amount of force, effort that you're putting in is less. So that's how ramps work. The answer being D right there. I love this problem, I think. Go ahead and do 12. I feel like 12 we didn't do a lot in class. We needed to. I have a gift for you, Danny. Some homework.
You can be.
Where was it?
I don't even remember.
It was in my car right now, and I was like, why is it in my car? Oh, I think I know what happened. I think you left it here yesterday during the Inspires meeting, and my wife has the same lanyard, that Riverside one, and I thought it was her lanyard. Because it was in my car, and I was like, Daniel's never been in my car. Again, Daniel's never been in my car. It's on record. this is what it was originally, and then it became 2Q. And this is the part where I think it went wrong. This becomes 2Q.
What?
What happened to the other two?
So, this is how they were, right? We have two spheres,
Oh, that's.
and then when they touched, this one dropped. When they touched, this one lost 3 positive charges, and where do those positive charges go?
Into the other one.
Into the other one. So the other one had a -1 charge,
Oh my
and
god.
then it gained 3 positive charges, so it went to
Ends up
+2. So that's the change that I went to, and then we can do our math. So when this one went from 5 to 2, how did it do that? By multiplying how? So how do I go from 5 to 2?
Yeah, but 24.
It's always easier to do it in fractions, and this is like some dimensional analysis stuff. I want to cancel out.
Times 0.4.
Yeah.
So it becomes D8. Well,
You guys are all saying 0.4? Is that the answer?
so that's the in
Oh,
fact-
0.4, yeah, yeah.
Yeah, in fractional form, so it'd
So-
be
This is the way I always do it. And you guys can, however you guys got 0.4, because you guys are super badass, that's cool. But here's a strategy. I want the 5 to cancel, right? I want the 5 gone. So I'm going to put the 5 at the bottom. And what do I want to be left over? Top 2. So when I multiply these cancel out, leaving me just with 2. So that means this one got multiplied times 2/5. Mind blown?
Yeah.
That's some like chemistry stuff right there. In dimensional analysis, that's how you.
that's actually quite literally how I figured it out. Like I
That's how
thought that-
dimensional analysis works. From moles to grams to like whatever you need it to. Whatever you want to cancel out goes at the bottom. You're welcome, AP Chem. So how do you? This one's easier. How do you go from -1 to 2? You multiply by -2. So you get 4/5. But they said they only care about the magnitude. So the answer becomes B. Don't try 13. Let's see what it says. I saw rotation or inertia kind of stuff. So it has a rotation or inertia of 2. At the instant the wheel has a counterclockwise angular velocity of 2 radians. The average counter torque is I, and continues for. We can do this problem. Heck yeah. Kind of.
Was that one, I remember I zoned off in the last one as well. I kind of like zoned off and I started going through their sheet. And then I saw that rotational stuff and I was like, what is that?
So
I wonder how to use it in like,
what they're asking me to find the change in angular momentum, right? What is the change? I mean, just remember, angular just means going in a circle, but everything else is the same. So how do I find change in momentum? Japfat. Japfat. Force times time. Now here's the part where my first period is a little bit ahead. Change in momentum is going to be, every time we see the letter M, we no longer use M, right? What letter that we use now? No, well, M used to be a measure of inertia. So every time we see M, now it's I. So IF minus, that gives me, and instead of using T now, this is where my first period's a little bit ahead. What do we use? The tau.
yeah.
What does tau stand for? My first period's like 15 minutes ahead of my second period. The torque.
Yeah.
T is the torque. So they give us a torque. The torque is 5, and that torque was applied for 4 seconds. So the change in momentum will be 20. Torque is the force that makes things rotate. So force times time will give you change in momentum. Torque times time will give you the change in angular momentum. It's the exact same problems, the exact same physics, except things are spinning. I just wanted it to spin. A student, go ahead.
It says counterclockwise, would that be like a negative?
Yeah. A student uses a spring scale to exert a horizontal force on a block, pulling the block over a smooth floor. The student repeats the procedure several times, each time pulling the block from rest through a distance of 1 meter. Which of the following graphs of force as a function of distance of time will the block be moving the fastest at the end of the 1 meter? Woo-wee! I love this problem right here. I'm trying to get you guys excited. So what do all of these force, we have force times distance graphs. Shit, yeah. We should know what do these give me?
Work.
Work. Hell yeah. And what is
The
work?
one with the biggest curve area under the curve will give you like the biggest force, and then it's like kind of
Well, not the biggest force, the biggest change in energy.
change in energy.
Yeah. Work equals the area under the curve. The biggest area under the curve is the biggest change in energy. And they all start from what?
Right.
From rest. So the final is going to be the kinetic energy. So work equals change in kinetic energy force times distance. I'm just going to put it there, but so we have work equals 1/2 mv squared minus 1/2 mv squared initial. The initial is going to be 0, so we can, the work is going to, the area under the curve is going to equal to the final kinetic energy. And if they all have the same, if they're all the same object, the one with the most kinetic energy is the one going the fastest. So which one gives you the biggest area in the curve? B, you're right. You are correct. I know it's been an hour and we've only done roughly about a third of the test because we're going slow and I'm adding a whole bunch of extra stuff to each problem. But what do you guys think about these problems now? Break them down. Try like, what do I know? And I know I'm really leading you, so it's going to be completely different when you're there by yourself. But that's why you guys got to do practice problems. You guys have a whole practice test at the back of that book. You don't have to take all of it. You can just take like the first couple of questions. $18 days. 11 school days.
Wouldn't Monday already be like 10?
No, because I'm counting. There's the Monday before the test because it's on a Tuesday. So you have this week, another week, and then a day, and then the test. So projectiles fired in the air explodes and splits 2 halves of equal mass that hit the ground at the same time. If the projectile had not exploded, it would have landed at point X, which is a distance of r to the right of the launch point. So let's start. Well, let's read it, because I'm already getting confused. Which is the distance of r to the right of the launch point. After the explosion, one of the halves lands at point Y, which is a distance of 2r to the right which is the distance of 2r to the right of the launch point, if the air resistance is negligible, where the other half land. Alright, so let's draw this. Pictures are your friends. So if this thing launched this way, it would have landed right here. Cool, right? That's what they tell us? But instead, it went this way, exploded. After the explosion, one of the halves lands at point Y, which is 2r. Did this bother you guys?
No.
Does it bother me?
24.
Oh, the 24 bothers
Yeah,
you?
Just one part too.
Alright, so that's what happened. One of them went that way, and then the other one went this way.
So then what is the other one like?
On the opposite side.
Man, I'm about to shoot myself in the foot here. We're gonna skip this one. This is a center of mass problem. Remember I said we were like a week behind? One of the things the thing that I decided to skip was center of mass and centripetal force. I cut it down from like 4 days to like that 1 day. Center of mass, there's 2 rules to follow. And at the end of the very last day, not the last day, like the last Friday, I'm going to show you a couple of videos for center of mass that will show you that those 2 rules to follow for center of mass. But anyway, the answer is B on this one.
Oh.
I'm gonna assume right now that it's one of the things is like they're equally the force is equally distributed.
Yeah. But let's go ahead and go to D, 16. An elevator carrying a person of mass m is moving upward and slowing down. How does the magnitude of F, the force exerted on the person by the elevator, compare to the magnitude of mg of the gravitational force? So I feel like we talked about this just this week. So go ahead and try this one. Picture what's going on. Draw free body diagram. Slowing down but moving up. What does that mean? You got it?
What's the answer?
That's exactly right. Woo! That's a good force column right there. We rocking and rolling, people that are not here. I don't think I have one next week planned, right?
You don't?
I don't know, I gotta look at the calendar.
I thought you said it was every Saturday from now on.
Yeah.
Was it? I had to look at the calendar, cause it was like first come, first served for the AP calendar, and I came in first, so mine got served first. But I'm not sure when I stopped, cause I didn't wanna seem greedy, and I wanted to leave some for Gallegos, so I gave, Gallegos test the second week, so I gave him that Saturday and the other
This is
Saturday.
May 5th.
He took all them, but I thought he had two, I don't know, look at the calendar,
Oh, okay.
cause but, let's look at this problem right here, so we draw a free body diagram, what are the forces?
And
Mg
No, of course.
and the normal force. And the normal force, they don't call it the normal force in this problem, but we know the normal force is F, what they're talking about right here. So, let's talk about this right now. Which direction is it moving?
Upward.
Up. So, positive or negative velocity?
Positive.
Positive velocity. And it's slowing down, right? So what can you tell me about the acceleration?
Negative.
Negative acceleration. So if I have a negative acceleration, what does that tell you?
Force, that force is worked down.
You have a negative net force. So what force is going to be bigger? Mg is going to be bigger than Fn.
The thing is that it isn't FN because it's in that elevator, so technically it's in free fall, no? Because it's tension that's actually pulling it
Well, that's the normal force of the object inside of the,
up of the actual.
but yeah, the point is, if you didn't want to think about it as the normal force and you were thinking about it as the tension pulling up the elevator, you could have that way. So maybe that's why they didn't give it a, alright, I was thinking of a person inside the elevator, but
I was thinking of the actual elevator.
the actual elevator,
Yeah.
same methodology, you
Just-
explained it exactly right. Questions on this one? How did we do on this one on your own? Better? I feel like a week ago, not so hot maybe. I feel like this is working. 17, force times time, force times time, God. What should I be thinking, force times time in this problem? Impulse, and what is impulse? Japfad, which is change of momentum. A soft block of mass m slides without friction in a positive direction with the speed of v. Why don't you guys go ahead and read that, try that out. Probably my wife texting me. Eric, are you excited for Kanye's EP?
oh yeah.
I don't know if I am.
Why?
What?
You
I'd rather have an LP. I'm like 7 songs, bro. Take your time.
That's
Give me a whole album. I don't need an extended play. I need a long play.
Yeah.
Ooh, this problem's good. Are you like signaling me to go check your work?
No, I'm like the little dogs is like confused at the deal. I don't know if I got that right now.
No.
I remember if this.
No. And this is a good problem for this misconception that I think a lot of people are gonna have. all positive impulse, right? So we have impulse equals MVF minus MVI, right? So if this is positive, is my final bigger or smaller? Okay, final number, initial. If this is positive, my final should be bigger or smaller? I want this number to be positive. So this is going to be bigger or smaller?
This one should be bigger.
Yeah. So your final velocity needs to be bigger than your initial. So you're actually gaining momentum, not decreasing. Because the impulse is positive. So that's why they should be out, these should be out. And there is a change of momentum because there is an impulse. And I feel like a lot of people think just because it's negative doesn't mean that there's no, I'll point that out, and I'll point that out with work also. So, what do you guys get? You got what?
B,
It is B. How do you get B?
well, because there was a force in the positive direction.
Okay.
So like, if it was, the force was positive and it went faster,
That's,
so like, the impulse had to.
that's one, okay, so you're saying the force was positive, so the force was to the right, so it must be increasing its speed? But that's only true if it was moving in the positive direction, which they tell you it is. So we have an increase in velocity. Increase in velocity means an increase in the momentum, so positive change of momentum. That's a good logic right there. I really love it. Good logic. Not the route that I'm going to explain, but it's solid and it works. So the change of momentum looks like this, right? So this is the impulse, right here. So is that positive or negative impulse?
Positive.
Positive impulse. Negative impulse would be down here. With me? So I have positive impulse, I know that's positive, and that's going to be equal to my change of momentum. So Eric, if I want this to be positive, which of these two numbers is bigger? The final or the initial? The initial is going to be bigger? Let's try that out. 10, and let's have a number over here. 9 minus 10. So, yeah. So my final has to be bigger. Even if it's just a little bit bigger, I still get a positive number, right? So my final is bigger because I have a positive change of momentum. So positive change of momentum is going to be an increase in momentum. So the answer is B, because that A says that there's a decrease in the momentum.
I don't get the way you did it.
The way I did it? Okay, so let's say that the areas of the curves were the same right here, right? Let's say the areas in the curve are the same right here. What was my impulse then?
0.
0. So that means that these two have to be what?
Equal to.
Equal to each other, so no change, no momentum. Now, if I only had, let's say that it looked like this, what can you tell me about my impulse? The impulse is negative. So how am I going to get a negative impulse? The final is smaller. So if the final is smaller, I know that my speed is decreasing. My momentum is decreasing because it started big and then got smaller. So the other one is opposite. I know it's positive. I know it's positive. So there must have been an increase in momentum from the initial to the final. There must have been an increase. Yeah? Which leads me to like work. Let's go to work. Work equals change in energy, 1/2 mvf minus 1/2 mvi, change in kinetic energy. So let's say this is distance. This doesn't mean the object is slowing down right here. The object is speeding up. The work done every second is less. So that means every second it's speeding up a little less, but it's still speeding up every second. Right here was speeding up a lot. Right here it's speeding up a little, but both times it's still speeding up. Why? Because I have positive work. This whole time it's positive work. So that means in order to get positive, the initial must be smaller than the final, so there has to be an increase in the velocities. What are you going to say?
Like when you push something, like you push it and like you like stop pushing it, but it's still like moving.
So it's like I'm pushing an object that's with all my might, and then I get tired, but I'm still pushing it, just not as strong before.
Oh, okay.
So it's still speeding up, just not that, it's not speeding up as much as it was before. The acceleration is smaller. The change in V is smaller, which is acceleration. Force times distance on 18. A cart is moving on a level track in the positive direction. A force acting parallel to the x-axis exerted on the cart. The graph below shows the net force. This problem's awesome. What is the net change in kinetic energy? It's like these two problems were put next to each other on purpose, which they were. So how do you find the net change in kinetic energy from this graph?
What happened to B squared?
Well, look, what kind of graph is this?
Force.
Force times distance. And what do I get from the area under the curve right there?
Work.
Work. And what is work?
Change in
Change in energy.
The change in energy. And isn't that what they want me to find?
Yes.
So what is the answer right here? What do you say? D? Why D?
But it's B.
This is a good, this problem, like, I'm so glad I did this explanation because it exactly compares to this one right here. Well, let's look at this right here. Looks like this. Where this is 5, 10, negative 5, 2, and 4. So what's the area under the curve right here, Megan?
20.
What's it down here?
10.
Not 10.
Negative 10.
Yeah. Negative 10. So when I find the when I get the change in, when I get the area under the curve right here, what's my area under the curve then?
10.
Positive or negative?
Positive.
Positive. Positive 10 equals 1/2 mv squared minus 1/2 mv squared. So was there an increase or decrease in the velocity?
Increase.
Increase, because that's the way I'm going to get a positive number, right? If my final is bigger. So that's why the answer is B and not D. If this number was negative, then I would have a decrease in energy because I'm slowing down, a decrease in the kinetic energy.
go ahead and do the next two, and then we'll take our first break.
So let's take a pause, let's do 19.
So what kind of vert table do you guys make? With one or three or two resistors?
I went ahead and did one with 2 resistors, and let me tell you why.
The first resistor being 4 and the next resistor being 16. And then 12.
And because they told me that R1 and R2 are equal to what? 16.
So this vert table this vert table corresponds
To that.
where I know that this one's 4 and I know this one is
16. You guys see what I did, why I did it my way? So now, what do I know about the current right here?
it's 2. So you're asking me to find the current right here. So you're like, well, what would you guys like to have done to make this really easy for you? What do you need? What were you guys? Well, I don't know this, so how am I supposed to figure it out? What do you guys want to know?
The total resistance?
The total resistance? That would have helped you? Why?
Or, I just thought that was like one of the first things that I could find.
Well, what are they asking you to find?
The current in the right branch.
They're asking you to find this right here, right?
So if we knew the voltage for number 2, would it help?
Yeah, that'd be good if we knew the voltage for number 2. But wouldn't it be cool also if we knew the total current? Because what do we know about when they're in parallel? The current splits. So 2 went this way, some came that way, and then back here it all comes back together. So I know these two have to equal to this one. But I don't know what the total current is. But I know this relationship.
Can you just multiply 4 times 2 to get the voltage? Because they're both gonna have the same voltage.
Oh, that's one cool way to do it.
Product over sum,
Well,
and then
go, I'm sorry, Megan. Let me go continue with this idea. You found the voltage here,
Yeah,
which gave you 8.
and it should be equal to the other,
Yeah. And you said the voltages should be, they're in parallel, so they have the same voltage drop.
so this is also the total is gonna be 8,
The total right here is,
0.5.
what?
That's gonna be 0.5.
This one's gonna be 0.5?
Yeah.
That's true. Dang, dude, good job. That's not the way I did it. I like it when kids do it different ways. So, do we see what he did? That's cool. Now we know the voltage of the battery, the total voltage, and then we can solve for the. Dang, that's sweet. This is the way I did it. I don't want to erase that work, so I'll have it 1, 2 total. 4, 16, 2. So, do I know is the current gonna be bigger or smaller over here?
smaller.
I know it's smaller. So I know it's gotta be smaller than 2, so D's out. How much smaller? And it comes back to Vert. How much more resistance is over here? 4 times less resistance, so this side's gonna get 4 times less current. So 2 divided by 4 gives you 0.5. That's the way I did it. On 20, they swap out resistors, and they swap out the resistors 1 and 4. So now we have this weird vert table, which you tried to do, and it's the answer in this one is actually D. Unless they give you what R2 is, this problem's kind of impossible because they told us that R1 plus R2 gives us 16, right? But for all we know, R1 is 1, R2 is
Wouldn't it
15.
be A though? Cause like the total resistance doesn't really change. They just.
But it says that it
The-
doesn't say the total resistance, it just says the resistance.
How does the current through the battery change?
Yeah, it seems like the resistance doesn't change, the current stays the same.
It just says,
They're
It-
just swapping.
Well, the total resistance might change.
How though, if you're just changing the order in which they are in?
Well,
so we don't know the values of
Because-
R1 and R2.
let's just try and hopefully it comes out. So we had, let's do it this way. This is the best way I can think of doing it. switched, right? So, I mean, this must stay the same, right? So if I move this over here, this gives me, let's say that this is 1, and this is going to be 19. Is my total resistance going to be the same between these two?
But that's not what they're saying though.
So, that is what they're saying. So they're saying,
No, they're just saying that they swapped them. So they just changed like the position of the thing.
so this one's 4, right?
Yes.
These two equals 16, right? And then they swap these two, right?
Yes.
So now this one is,
That one is 4,
this one is 4,
and the other one is the other one.
the other one is what? I don't know, right?
Yes.
So what I'm saying right here that this is 1, so what was this before? What is this? 15. Because it used to be 1 plus 15 give you 16, so I swapped them out, so now what do I have right here? 19 and 1. How did I add these, how did I get that 16 right here?
So the other, the R1 and R2.
Because they're in series, right?
Yes.
But now I flip R1, I flip these two, that's what they told me. So the 4 resistor went over here, and the 1 resistor went over here. So now the resistance over here is 1, and right here it's 4. So the total resistance in this branch is 19. Yeah? If you do product over sum for these two, you're going to get a different total resistance. So if they have different resistance, but the same voltage, then the total current is going to be different. Yeah? Does that make sense? And so let's do a vert table. If we're doing a vert table right here, the V's are the same, right? You're with me there? The total R, the RT, would be different for both of them. Are you with me there? Or do you not see why that would be?
Yes. Because the other one is in parallel, so it adds up differently.
Yeah, so the totals are going to be different, so that's why the I's are going to be different.
Okay. So wouldn't like the totals would be like,
Do product over sum right here, and do product over sum right here, and tell me if you get the same number.